Can I explain labeling and the address? Okay, so we can do that. Hmm? You mean for exam one? For the lab. Okay. So, all right. So let's go back to the lab, which is due today. Okay, so it's due sometime before. Okay, I'll put it this way: it's due before tomorrow. How about that? All right. So the lab is this one, and if I do a preview, I can look at questions five, 4, 5, and 6. Is that what you were asking? Which three questions? Yes. Okay. Okay, so let's deal with question number 5. So the question is actually not just a question because the question is actually part of the instruction as well. So, so I'll just kind of read this out, like sentence by sentence. The assemblers accept label definitions, and the way you define labels or the purpose of labels is the same as labels in C and C++. So the reason why you define labels in C and C++ is because you want to be able to say, okay, I want to continue execution at that point. Now, you already know that your C professor does not like you to use gotos, but in this class, that's the only way we can alter the direction of execution. So that's why we need to rely on labels. Okay, so next sentence. This is a handy feature because otherwise the programmer, being you, will need to count the number of bytes used in code. A label definition, now this is the important part, is basically an identifier. It's just a name, but we can use the same syntax as a C variable name, followed immediately by a colon, which is the same as how you define a label in C and C++. A label definition must be the first thing of a line, and there should be nothing other than comments starting with / after a label definition. So you basically start a name, okay, starting at the very left edge of a line, and then a colon, and nothing else to the right-hand side except for / and then comments. Yep. Well, it says right here, can be any identifier using the same rules as a C variable name. So you can start with underscore, you can name your variable underscore, you can name your variable underscore underscore, and so on to make your code basically not readable. Okay, so the following defines label L1, so it's really just L1 and then a colon. Okay, that's the definition of the label L1. Why did I use the name L1? Because it's label 1, okay? You can choose anything you want as long as it is still following the rules of labels or identifiers in C and C++. Note that a label is a symbolic name, okay, so this is the important part, of the address of the next byte, okay? What bytes are we talking about? Instructions, okay? Every instruction is going to take up at least 1 byte, and some will take up 2 bytes. In other words, if in the following code, okay, here's the following code, L2 is the symbolic name of the address of, okay, to be very specific, it is the address of the first byte of the LDI instruction because the LDI instruction takes up 2 bytes. So when you have 2 bytes and each byte has a unique address, then what is the label corresponding to? It's corresponding to the first byte. Okay? So do we have any questions about the text up to here? Is there anything that is not clear? Yep. The second byte is going to be just whatever L2 is and then plus 1. Yeah, so it's just adding 1 to that label. Yep. Okay, so the last paragraph says, assuming the above code is at the beginning of a program, in other words, you do not have any code preceding that, you can have any additional code after that if you need to. What is the value represented by the label L2? So the value represented by the label L2 is really asking what address is L2 representing. not what is the content at the address. It is what is the address that L2 is representing. In other words, once you define a label, every time the assembler sees that label, it replaces the label with the value that the label is defined to, which turns out to be the address of a particular byte. So that's the question. So what else do we want to talk about? I mean, do you guys know how to answer the question now, or do you not know how to answer the question? Okay, to quote Yoda, do or do not, there's no try. So which way is it? Do we know or do we not know?
So we use the assembler sheet.
You can use the assembler sheet. Yes, that would be highly recommended to use the assembler to assemble this code, just these 3 lines. Erase everything else on column A of the source tab. Paste these 3 code in onto 3 separate lines. Okay, look at the assemble tab. Particularly pay attention to columns W, X, and Y, and refer to the previous lab of what those particular columns mean, and the answer should be there.
The row for the last line?
For the last line, what do you mean?
No, there are, on W there are many rows, yeah? On the W column.
W, X, and Y, yes. But there will be only 3 rows of those columns that will actually have values.
Yeah, I mean, is it the third row that we are looking the value for?
You kind of have to figure it out by yourself, because each row is corresponding to 1 line of this code. So there's one row corresponding to LDI A12, which tells you the address, the first byte, and the second byte of that particular instruction. So your question is, what is the address of the first byte? Okay, I don't think I can go any further without actually telling you the answer. Okay, so it really is asking you, do you understand what the assembler is doing? Okay, if there's no assembler, okay, if there's no such tool, and you are left to implement these instructions, how would you do it? What is the meaning of a label? Why do we need a label? Well, it's because otherwise we'll have to do all the counting, which is very tedious. It's much better to leave it up to a tool to do all the counting, and we just have to remember the names of a particular byte, the address of a particular byte. So that's the whole idea of a label. Okay? Any other questions about this one? Okay, so instead of me trying to answer the question, how about this? You guys try to do it at the lab after the lecture, and if you still have questions at that time about the concepts, about what is described here, then I'll try to answer those questions. Okay? All right, so the next question, do we have any question? Do we need any clarifications of the next question? Hmm?
It's not clear.
It is not clear. Okay, which part is not clear? You have to tell me which part is not clear. Say again?
Halt.
The halt instruction. The halt instruction is where it will stop. Did I explain the halt instruction last time? Or not? I think the halt instruction, but I did talk about the pseudo C code for the halt instruction. It's a forever loop, which means once you get to the halt instruction, it cannot proceed any further. Okay? So besides that, are there any other questions? How do we know whether the program gets to the halt instruction or not? Okay, how about that one? You're running it, Okay, first of all, even though it doesn't say it, you need to run this code in the simulator to get to the answer. Does that make sense? Because if the question says when the program gets to the halt instruction, what is the value of a particular register, you cannot, well, okay, I can, but you cannot stare at these instructions and just kind of run the simulation in your head and know the answer. So the implied instruction is you have to run it in the simulator. If you run it in the simulator, how do you know that the program is now at the halt instruction? How do you know that? There are at least two clues that will tell you that. One clue relies on the fact that you know what the halt instruction does. The second one does not. Okay? Shall I talk about the second one first? Okay? So when you assemble this program in the assembler and you go to the assemble window, what do you see? What do you see on column W, X, and Y? Okay, what is column W in the assembler? In the assemble tab of the assembler? The addresses, very good. And what is in column X? If a row corresponds to one line of code here, except for the label definition, it definitely has content in column X. So what is column X on the row? Okay, the byte of the opcode, right? Okay, so and which register in the processor tells you which instruction it is about to execute next? That's from the previous lecture. In the previous lecture, we went through some simulation of how a program executes. We actually went through the processor simulator itself. So which register will tell you which location in RAM contains the next opcode to execute? Big hint, its name has counter in it. Program counter, very good. But there's no such register called program counter in the entire design. Why? Because it's abbreviated. What do you think it is abbreviated to? PC, very good. Okay, so using the PC, using the assemble tab of the assembler, particularly columns W, X, and Y, how do we know that we have reached the halt instruction? The program counter always shows the address of the next instruction that that the processor should execute. And what do you think is the address of the halt instruction? 0. No. The halt instruction, go ahead. Yep, so whatever L1 is going to be the address in the program counter when the halt instruction executes. Okay, so how do we know the program counter has gotten to that point? Yep, we just look at the program counter. The value of the program counter is on the register itself. Okay, so you're going to have to pull all those pieces together and kind of run the program that way. You would also that would be the other way to notice is you go full speed simulation and you look at the program counter, it doesn't change anymore. That would be a very clear indication that you have reached the halt instruction. So there are two ways to find out. One requires single clocking, single tick, Control T, Control T, Control T until you get to the program counter to whatever L1 is defined to be. And the second one is just Control K. Let it zip until the program counter doesn't change anymore. Then you either stop the clock, you don't even have to stop the clock, and then you just right click on the register bank, go in, and then look at the content of register B, and that will be the answer. You can continue to step as long as you want. It's not going anywhere. Yep, it will stay there. Because I think last time we had a chance to talk about the halt instruction, if I remember correctly or not. I didn't do it? Okay. But anyway, even if the halt instruction is a no op, we can still catch it. Because you know what the address is, And then once you know what the address is, you just have to match the program counter to the address of the L1 label. And when the program counter is at the L1 label, then you know that you have reached the halt instruction. So that one is always reliable. Okay? So are we good with number 6? Okay. All right. So let's go to number 7. Okay, so number 7 is kind of the same deal. Okay, so I'm just going to read out the instructions here. In addition to specifying opcodes translated from mnemonics, so LD, LDI, ST, those are called mnemonics. Those are symbolic name of opcodes. A program can also be specified using a program can also specify the value of a location using the byte directive. For example, the following code allocates and initializes 3 RAM locations to spell out TAC using ASCII code. Because 84 is uppercase T, 97 is lowercase a, 107 is lowercase k. So by using these 3 byte directives, I would be spelling TAK out. But you can also use it to spell out opcodes. Currently, the assembler can only accept the use of base 10 unsigned integers, and only 1 byte can be defined per byte line. So that's why it's kind of tedious, because you need 1 line per byte. The byte directive can also be combined with the use of label definition. So in the following code here, L3 is the label, the symbolic name of the byte that contains uppercase T of TAK. Is that okay? So one thing you can do is really just copy and paste this code into the assembler, and then look into the assemble window or assemble tab and see what are the content, of the program, and also look at what label L3 is defined to. Okay. And the mysterious part is L4 colon label, byte L4. How does that work? Well, L4 by definition is the symbolic name of the byte that is after the label definition. So L4 is the address of the byte, okay, that is defined after that. But what is the value of that byte defined to? Well, it's defined to be whatever L4 is. Well, is that a problem? No, because the assembler just counts, right? So let's say we have no up, no up, no up before L4. The first no up takes up 1 byte, the second no up takes up another byte, the third no up takes up another byte. So those 3 no up instructions would take up locations 0, 1, and 2 respectively, which means the byte is going to take up location 3. Okay, so that means L4 as a symbolic name, as a label, is defined to be 3. Every time the assembler sees L4, it means 3. Okay? So that means byte L4 is really the same thing as byte 3. It's going to allocate 1 byte at location 3, initialize the content of that RAM byte to 3, which is 0, 0, 0, 0, 0, 0, 1, 1. That's it. That's what the assembler is going to do. So are we okay with that? The mechanism of how labels are defined. Okay. So the following code, okay, so this is the real part of the question, is you can actually write an entire program using the byte directive if you do all the assembling yourself, which is painful, and that's why we don't do that. But just to illustrate that you can do it, we can do it like that. So there's a whole bunch of code here. If you want to disassemble the program, you can actually translate each byte back into the binary bit pattern, look up the opcode table, and figure out what opcode we are actually defining here, and then figure out the behavior of this program and answer the question without actually using the simulator. That is entirely possible. I'm not recommending that at this point of this class, but it is possible. So to answer this question, what we need to do is to copy and paste this code into the assembler, okay, and run that program. When it doesn't go any further, which means the program counter doesn't change anymore, which means it has reached a halt instruction, although you cannot actually see the halt instruction here. I just want to know what is the content of register B at that time. That's the entire question. Yep.
So we
Yes.
Then we load it from the RAM,
Yep.
and so then do we just look right away the register B, or do we run the program first?
What do you think? When this program cannot go any further, how do you know the program cannot go any further?
We should press Control T until it doesn't
You
change.
type Control K to let it rip as fast as it can. You observe, you eyeball the program counter. If the program counter stops moving, then it's not going any further.
For the previous also we do the same for the number
Yes.
6.
Now, for both programs, once you really understand the instructions, you really don't need to run the program to find out what it's going to do.
Yeah.
But for this particular exercise, the intention is for you to run the simulator to find out what it's supposed to do. So are we good so far? Okay, all right. Okay, so so if this is okay, we are gonna stack on this one a little bit because today I'm gonna give you a new assignment. So there is an overlap a little bit of the lab activities. So today I'm giving you a new lab, which is simple branching and code analysis. So we'll take a quick look at this one, and we'll do a preview. All right. So this one relies on a few instructions that we haven't seen before. One is the increment instruction. And let's see, I'm going to move on to the next question. The next one is a JMPI instruction. And then we have the compare instruction and a JCI instruction. And let's see what else. On the third question is really long, because it's really trying to explain, how you can trace the execution of a program. And I'll do something like that in today's class, but it's not going to use exactly the same code. And then the last one is giving you a big chunk of code. And you have to find out, what conditional branch instruction would result in a particular register being, incremented the most. Okay. So in the following space, write down which conditional branch instruction you choose and the actual number of times that the no-op instruction of label L2 is executed. So label L2 is right here. So the question is, you have to find a way to count the number of times that this instruction executes. So you can do it by Control T, okay, which is going to be extremely tedious and highly not recommended, or you can use a technique that is actually talked about in the question itself. So the question itself is going to give you a tool to do that. And you also have to initialize these byte locations to your student ID. So everybody has a slightly problem to work with in this case. And that's it. That's the entire quiz. So what we need to do in the lecture today is to talk about the instructions that you will need to know. And particularly, I can just focus on this slide here because this slide has the inclusion of all the instructions that you need to know. The LDI instruction we have talked about already. Okay, so if you did the lab, you should have an understanding of what the LDI instruction does. You can also look at the opcode table or the assembler manual. Both of those would explain what the LDI instruction does. All it does is to initialize a specified register to a specified immediate slash, if you want to call it constant value. And that's all it's going to do. We talked about the label. So now we can talk about what is the increment instruction. Increment B is really just what it says. B is now one more than before. That's it. Register B is going to be incremented by 1. So is that okay, what the inc instruction does? Okay. And then we have the compare instruction. What do you think the compare instruction does? Well, let's check out the okay, let me go to the share folder so that we know where to find that information. All right, so we go to the shared folder and then go to the processor subfolder, which is here. And then we look up either the assembler manual, so this will work, or you can also, for a more concise description, you can go to the opcode table. That will do the trick as well. So it's up to you. If you want something that's more concise, go to the opcode table. If you want a more thorough understanding, go to the assembler manual. Okay, so here's the opcode table. And okay, there we go. I'm going to zoom in a little bit. And we want to look up INC for increment. And increment is a kind of later added instruction, and this is the description of the increment instruction. So the opcode is 1101XXXX, which means whatever register you're incrementing needs to be specified twice in the opcode. If you're incrementing, let's say, let register B, which is 01, then the actual opcode in RAM is going to be 11010101. Or in hexadecimal, that's going to be a D, because 1101 is 13, which is D, and 0101 is 5. So D5 in hexadecimal specifies the opcode to increment register B by 1. Is that okay? So when you look at the explanation here, it's just plus plus X. Okay, it's just an increment. And that's all it does. What about compare? Well, let's go find compare on this sheet here. I think it's probably already on the screen. Maybe not. Right here. There you go. So here's compare. And compare looks a whole lot like subtraction, but it's not subtraction, right? Look at subtraction. Subtraction is x gets x minus y, and then compare is just x minus y. What are we doing with the difference? Nothing. We just perform the subtraction. But if we're performing the subtraction without storing the difference, what good does it do? It sets all the flags. Remember the flags? We have the Z flag, the C flag, the carry, which is also known as the borrow flag, the overflow flag, the sign flag, and also the L flag. Those are the 5 flags that we can set using a compare instruction. Okay? So the compare instruction doesn't store the result of a subtraction other than setting the flags accordingly. Is that okay? So X is the minuend, and then Y is the subtrahend. So XX is going to specify the 2 bits for the minuend, and then YY will specify the bits of the subtrahend. So we good so far with the subtract instruction. Compare. Question? It's good? Okay. All right. So now we continue with all this code here. So we have talked about the compare instruction. So the real focus of today's class is really to talk about conditional branches and unconditional branches. One is JCI. JCI is one of the 5 conditional branches that can specify a destination. If you want to write down what JCI really means, it means continue execution if and only if the carry flag is set at the following label. That's all it's going to say. Okay? In other words, I'm taking notes for you. So in other words, JCI to some label, okay? JCI some label L1, okay, is really the same thing as saying if and only if the carry flag is a 1 or non-zero, go to label L1. That is the C equivalent code of JCI L1. So now the question is, but what if the carry flag is not set? What do we do then? Well, what do you think the C code is going to do if C is 0? It just continues. Yeah, exactly. Whatever is after the conditional code, the conditional branch is going to execute if the carry flag is cleared or has a value of 0. Is that okay? Now the mechanism of the JCI instruction is kind of tricky, but I'm not going to talk about the actual mechanism because I want you to be able to run the program first. Okay? So we have a family of conditional branch instructions. So that means, okay, I'm going to leave this one up here, but I'll just say JXI L1 is really the same thing as if and only if the flag X is a 1, then we go to label L1. So what can X be? Okay, so X is a placeholder of, okay, the 5 flags. Can be Z, can be C, can be sign, can be overflow, can also be the L flag. That's it. That's why we have 5 conditional branch instructions. So there's JCI, JZI, JSI, JOI, and then JLI. Those are the 5 conditional branch instructions. Are we good so far with this? More or less? Because I just want to explain the opcode in the form that you know already in C and C++. Is that okay? Any questions about this part? Yes?
Sorry, can you just say one more time what this ZCS announced the
First 2?
Yeah.
So Z is the 0 flag, which means the result after a computation is 0. So the Z flag is set if and only if the result is 0 after a subtraction, after an addition, after a shift, after any operation that involves the ALU. Yep.
So just make sure I'm understanding this correctly.
Yeah, go ahead.
If you did a comparison of 2 identical numbers, then the Z flag would be set and you could do JZI to do a conditional statement on checking if 2 numbers are equal?
You can always do a JZI, except in that case, the JZI would actually branch. Yep. If you're comparing 2 numbers that are not the same, you can execute a JZI instruction, but it will not branch to the label that you specify, and it will just continue. It would just kind of quote-unquote skip the JZI instruction. Yep.
What's L again?
L is the exclusive OR between the sign and the overflow flag. Yep, that's we talked about the L flag when we talked about binary comparison, which is right after binary subtraction. Yeah. Yep. So that's why in this class everything kind of stacks up. The concepts. It's really impossible for me to say, okay, we're not going to use any concepts in the previous part of the class. That it's just not possible. So that's why whenever we talk about the concept, it is really important to get it understood and make sure that we do not leave any confusion behind, because that's going to bite us big time. I'm just going to take row today just because. Okay, this is cisp310. I always forget. I print out all these row sheets, but I always forget to actually take row. I shouldn't say always, but most of the time. Okay, so getting back here. What about JMPI done? What does it do? What do you think it does? JMPI to some label L1 is really the same thing as just saying go to L1. That's all it does. Okay, it simply says continue execution at that label unconditionally. In other words, if you specify any opcode like immediately after JMPI without a label to get back to that location from somewhere else, it's useless. It's unreachable. Is that making any sense? Because every single time the processor executes JMPI to L1, it continues execution at label L1. Now, obviously, in a very trivial case, what if L1 is right after JMPI L1? Well, then it's as if the JMPI instruction is not there, right? Okay. So let's see what else is here that we haven't really talked about. The LD instruction we have talked about already. The CMP instruction we have just talked about, the JXI. Now remember this JXI, the X here, is a placeholder. You are supposed to change that to JCI, JZI, JSI, JOI, and JLI, and find out which one will execute label L2 the most often. So in case of a tie, you can just pick one, okay? But you will have to run this program like 5 times to figure that out. JMPI explained already. JMPI, no up, increment, JMPI, halt. Okay, so we have talked about every single instruction now at this point. So it's time to give you some runtime example because I think that might be helpful. Okay, so let's go to the assembler and we'll do some programming. All right, so we go to the assembler. And whatever I do in this assembler, you can actually see it when you open from the shared folder. Okay. So here's my source tab. So what I'll do is I'm going to write a program, but I want you guys to analyze the program with me to mentally find out what the program is supposed to do, and then we'll run it to confirm our theory. Okay? All right, so we'll start writing this program. We'll just do an LDI, let's try something that's really annoyingly large. So let's say 117. Okay. And then we'll define a label here, L1. And when we have label L1, we do a CMP. Let's do a LDI B with 1. And then we'll do I'm just trying to figure out, how to incorporate most of the things that we have talked about. Let's do a CMPI, CMP, okay, CMP compare. We'll compare register A to register B. And then we'll say JZI to label L2. And then we'll say decrement, we'll say decrement register A. And then the JMPI to label L1. And then here's label L2. And then the halt instruction here. There we go. So now we have this program basically written. But the first thing we want to do is really not to copy and paste the code and just run it through, because that doesn't really help you understand the instructions at all. So what we'll do instead is we're going to look at these instructions, and remember you can always comment in your program. Okay, / starts commenting, just like in C and C++. So you can always say, what is that going to do? Well, that really effectively is the same thing as saying register A gets the value of 117. Okay, there's not much to this instruction. So this one is pretty easy too. All it says is register B is 1. This one is a little bit awkward. All it does is to do A minus B, but it doesn't really store the difference anywhere. But it does sets the flags. Okay. What about this one? This one literally is saying if Z equals to 1, go to label L2. But it is right after a subtraction. So right after a subtraction, if the 0 flag is a 1, what does it mean? What is it implying about the 2 operands of the compare instruction? That they are the same. Okay. Now we know B has a constant of 1 by the time we get to line 5. So all that really means is, if A is 1, then we go to L2. That's all that's what it is saying. But the actual translation is if the Z flag is a 1, we go to label L2. Okay. And then the next line, is decrementing A. So that's fairly easy, okay, depending on whether you like the long form of this or the short form. Okay, if you like the short form, it's the same thing as minus A. It's just decrementing A. And then we have a JMPI to label L1. which is in C the same thing as go to label L1. And label L2 is after the JMPI instruction. So the only way to get to the halt instruction is line 5 actually going through the JZI instruction. Okay? So can someone summarize what this program is going to do? Mm-hmm. Exactly. That's all you're going to do. So we can actually do the same thing using a while loop in C. Okay? So now the question is, how do I know how many times it's going to execute line 6? You can do it in two ways. You can either theorize the whole thing and go like, okay, so how many times do I have to decrement from 117 so that register A becomes 1? The first decrement, it becomes 116. The second decrement becomes 115, and so on. So how many times does it take to decrement it all the way to 1?
160.
116 times. Okay, very good. So we can actually theorize the whole thing and answer that question if I were to ask you, how many times do we execute line 6 before we get to the halt instruction when we start programming, when we start to run the program from the top? But sometimes it may not be easy to figure out just by reading the code and understanding what it does. So you might need to trace a program using the simulator. Okay, so I'm going to show you a technique to trace a program so that you can post-process the output of this trace process. So the next thing we need to do in this case, okay, is to go to the RAM file. When you go to the RAM file, make sure that cell A1 sets V2.0 raw, because if it says anything else, that means your program probably has some kind of error. So then you go to File, and go to Download As. CSV is fine, TSV is fine, but I just choose CSV as a rule of thumb. But that's just mine. You can use TSV if you want. We'll call this one Loop. Okay. So this program is called Loop. And then we switch to Logisim. So let me close some of the unnecessary windows in Logisim. And this is the only one up. Do a Control R first. Every time you want to rerun a program, you want to do a Control R to reset the processor. But a Control R will also automatically reset RAM. So now you have to go to RAM and reload the content of RAM. Right click, load the image, and then go to the folder where your CSV file was saved. Mine was saved here, loop.csv, click open, and here's my program. So now the question is, how do I do all the counting? How do I trace it? You go to the Simulate tab or Simulate menu, and then you go to Logging. And we can now decide what we are going to log. What do you think are important things that we need to log just by looking at the left-hand side of all the things that we can select? The flags? Okay, so flags seem to be kind of important. Okay, so we'll choose flags. What else? The program counter, very good. Program counter is actually very important. Does anyone want to observe the register actually decrementing, changing the value as we go? No? Well, sure, why not, right? I mean, so we'll pick up register B. Register B is inside the register bank, and you can see how register bank looks like a file folder because it's a container of more components. So we can double click and just say, okay, we're interested in register B. Was it register B or register A that I decrement? Register A? Okay, so we'll pick up register A because register B is a constant of 1, so it's not going to be very exciting. Okay, so here's register B. And, well, since we can always rerun the program later on, we'll just say that this is all we want to track at this point. Okay? So we'll go ahead and look at each one. And you can also change the base of everything that you are logging. So you can see how they're all logged as base 2, which works okay. It's just a little bit difficult to read because it's just a whole bunch of zeros and ones. So you can click Change Radix in order to change the base. The flags will keep it as base 2 because we need to look at the individual bits, okay? But with the other ones, like the program counter, it is best to change it to hexadecimal or decimal. And then also with the register bank, it's best to change it to either decimal or hexadecimal. I'm going to use decimal this time because we specify 117 and then becomes 116 and so on. So it kind of makes more sense to look at it as a decimal number. So that's basically, we're only logging 3 things in this case. Now with the lab activity, you might need to log more things, but that's up to you. Okay, you kind of have to figure out how many things you want to track down. Okay. All right. Are we ready? Okay. What about the other tabs, up there, table and file? So table basically is the actual log after a run. Okay. So right now it's empty because we haven't actually run the code yet. File, on the other hand, allows you to save everything to a file, which is what I highly recommend. So I would just go ahead and go to File and select. You can name any file here. Anywhere, you just have to remember where you put that file. Okay, so I'll just call this loop log.tsv. Okay, now the extension tsv is not mandatory. However, the file is going to use a tab separated value format. So if you save it with the tsv extension, it will allow that file to be opened in Excel or other spreadsheet spreadsheet programs a lot easier. So you don't have to do all the specifications later. So I highly recommend saving the file with an extension of TSV. You click Save, and now we can close this window. Everything that we need to log is now set up. So in this case, we'll just do a Control K to start clocking. And you can see it's still working. And there we go. So you can see, if you don't see any activity in RAM, that's a pretty good indication that it's done. Okay? But if you're not convinced, you can always go to the program counter and see that the program counter is not moving, even though the clock is ticking. If you're not convinced, you can also go to the microcode count pointer, because you can see how the microcode pointer is enabled, and yet it is not clocking, it is not changing. So all of these things are indications that the program has reached the halt instruction. All right, so now that this is all done, we can take a look at the TSV file. So we'll first take a look at the TSV file using an editor. So it's under my temp folder. It's called loop log.tsv, and it's just a whole bunch of values, it's actually highly readable even in a text editor, because what we're seeing here is flags are the 5 zeros and 1s. The program counter is just 0, 0 for location 0, 0, 1 for location 1, and so on. And then you have register A going from 117 to 116 and so on. It's going to move itself down. Okay, so is that okay so far? Yep.
Can you just remind me of the 5 flags?
The 5 flags in here. So the ordering, so instead of telling you which one is which one, which I cannot remember, I'll show you how I will figure that out so that you can follow the same steps to figure it out. Okay, so we have bit 0, 1, 2, 3, and 4 here. Okay, so you just need to find out, okay, which bit is which register. That's basically what you want to figure out. So the way to do that is to go back to the design. You go to the flags register and then figure out how it is connected to the ALU. So right here, you can see the flags register, and it is a 5-bit register. It is connected to the output and also the input of the ALU to flags out and flag in. So the next thing is to look into the ALU, go to that particular output pin or those particular output pins, which is flags out here. And you can see that bit 0 is carry, bit 1 is the 0 flag, bit 2 is the sign flag, bit 3 is the overflow flag, and then bit 4 is the exclusive OR between the sign and the overflow flag, which we know as the L flag. So that's how you can figure it out. If you cannot remember, you just go back to the design, go into the ALU and then figure out which bit of the flag is corresponding to which actual flag of the components inside the ALU. So are we good? All right. Cool. All right, so getting back to the analysis of the trace, okay? So the first thing we want to do is to go all the way to the end of the program and see whether it makes sense or not. Well, it seems to make some sense, right? Because register A got all the way down to 1, okay? We've eventually settled to location 0. Okay, the program counter is 0B. Now remember, the program counter is almost all the time 1 more than the opcode that you're executing. So that means we have a strong suspicion that 0A in hexadecimal is the address of the hold instruction. Okay. On top of that, we also we can see the flags is no longer all zeros. It was all zeros up to this point, and then it became 00010, which means bit 1 became a 1. Now, do you remember what bit 1 was? The 0 flag. Okay, that seems to make sense, right? Because after all, we said JZI, which means branch out if and only if the 0 flag is a 1, and it branched out. Okay. But prior to this moment, okay, you can see that we have a looping effect, right? Even on this particular slide or on in this particular editor portion, you can still see the looping effect because you can see how it went from line 2 or location 2 all the way to location 9, and then from location 2 to location 9 again. So it kept doing that, and then for each iteration, the value of register A decrements once. So you can kind of see the loop effect, right? Okay, so how do I count the number of times that we execute the decrement instruction? Remember, that was our original question because I want to show you how to use this technique. Okay? Okay. So then we need to look into the assembler and say, okay, I need to find the address of the decrement instruction. The decrement instruction is here. And we want to focus on columns W, X, and Y, particularly just column W. So column W says, the location or the address of the decrement A instruction is 07 in hexadecimal. But when you execute that instruction, or when the register has a change, which triggers a row in the trace, the program counter would have incremented already to whatever is next. So that means we are looking for rows in the trace where the program counter is 08. That's what we're looking for. Is that making any sense? Yes? No? Maybe?
Can you explain it one more time?
If I just want to explain one more time, I can just rewind the tape and play again. In a different way. Okay, so which part is not clear? Okay, so what is the question? Because you didn't specify from where should I re-explain using a different way. Okay, so the decrement instruction is on location 7. Is that okay? But we know the program counter is going to be 1 more than that when the effect of the instruction, when we execute the instruction. What are the 3 cycles that we talked about last time about the execution of instructions? Fetch is 1. Well, fetch, execute, there's one thing in between. Decode. Okay, so that's very good. So fetch is when we go to RAM, grab that byte, put it into the instruction register. Okay. Decode has 2 things to do. So decode has to do with copying the instruction register to the microcode pointer and pad it with 4 zeros. And what? There's one more thing that decode has to do. Increment the program counter. So fetch, decode, which also increments the program counter, and then execute. Execute is the only one phase where things actually happen. Okay, so in this case, A is actually decremented by 1. So that means by the time we observe that register A is decreasing by 1, the program counter would have incremented already to the next location. So if the location of the decrement instruction is 07, the program counter would have been 08 by the time register A is changed. Is that okay? If it is not clear, there's one more way to explain it, but I'm not going to do it in class. To single clock this program and find out exactly when the program counter gets updated, when register A gets updated, and so on. Is it tedious? Yes, but that is also a tool you can use. Okay? All right? Okay, so now we get back to the text editor. So in this case, I need to count the number of times that the program counter is 08. Okay, so that means we have to, okay, let me go back to the beginning here. So this is the program counter. I want to count the number of times that it has a value of 8. And you can see how when it is 8, it actually has two, there are 2 clocks or 2 log entries when it is 8. Why do you think there are 2 log entries when it is 8? One corresponds to the change of one is before the change of the register. Register A is changed from 117 to 116 here. The log doesn't happen until something has changed. So there are 2 entries of 8 here. So why do you think there are 2 entries? Yep.
Because the PC changed from 7 to 8, which it
That triggers the
log.
Yep.
And then after that, 8 changed to 116, which is another
Yep.
log.
Yep, exactly. So that's why it is logged twice. So that means if you just count the number of times 08 is encountered in the trace, you would have double counted, which is fine. You just divide it by 2. Okay. So did everybody catch the explanation of why there are 2 lines of 08? The first time is because the program counter changes. The second time is because the actual execute part of the instruction. So that means the first one is due to the decode cycle of an instruction execution. The second one is due to the actual execution of the instruction. So are we good so far? All right. So I think that's, from the perspective of what the instructions do, this is all that we need to know for today's lab. Are there any further questions about these particular instructions? Yep.
Yeah. So in the end, in order to find out how many times decrement was executed, you just have to count these 8s, or is there a way?
You count them, the 8 and then divide it by 2.
Okay.
Because we know it's going to be double counted.
So just like put it in Excel or something?
Well, there are many ways to do it. Excel is one way, but since you will probably have a Google spreadsheet up already, you can also use that. You can also do that. So let me go to Google Sheets. So we'll start a new Google Sheet here. And the first thing we'll do is to import that file. So I'll show you guys how to import a TSV file into a spreadsheet in Google. It's really easy. So you just go to File and then do an import. So go to File, go to Import, and it will ask you to upload a file. Okay, so you click on Upload, and then select the file, and I got this one in the temp folder, and it's the looplog.tsv file. You click Open, and it's smart enough to understand that it's a tab separated file. You can always go ahead and select tab if you want to, okay, but it automatically knows that already. The second one, the last option, is kind of tricky. It asks whether you want to convert text to numbers and dates. I would suggest no, okay, because the numbers that we're dealing with, the one that we really need to know is in hexadecimal. So if you convert that into numbers and dates, sometimes it doesn't work very well. Now in this particular program, it's probably going to be okay, because the last location is only, I think, 09 or 0A, so it's going to be okay. But in general, the answer is no. So just click no in this case, and then click import data. And now you have the entire content of that particular trace in a spreadsheet. Okay. So in the spreadsheet, you can now use tools for counting purposes. Okay, so you can say there's a spreadsheet function called countif. Okay. So you can. I'm not going to show you how to use it. You can do some research. Okay. If you're in this class, you can do that kind of research. You do not need to be told how to use it. So there's a function called countif, and turn on formula help. So it says here, what is the range. So you have to specify, in this case, the entire column B. So that would be the range. And then the next thing is the criterion. In other words, it's asking you under what conditions should I increment the count by 1. Okay, so I'll give you the wrong answer here. Okay, just so that you know that it is wrong. So this is column B, and you can specify an entire column by clicking the column itself, like that. And in this case, I'll just say that it is. I've always wondered whether it can match like text, like PC. We'll see. Yep, it does. So if out of the entire column B, it finds one single cell that has a value of PC, which is from row 1 itself. So I'm not going to show you the code to find the 08s.
That's equal 8.
Hmm?
If it equals 8,
That's up to you to decide. Okay, you can experiment.
without the code.
You can experiment. But from this example, I think you guys know enough to get it to work. So this is why I really like TSV, because you can end up with a trace that has like tens of thousands of lines long. Okay, you're not going to go through that manually and hand calculate or hand count. Oh, where's that one? Where's the next one? Where's the next one? This gives you the tool to quickly look up or count, which ones meet the criterion that you are looking for. Okay, and you can even have conditions. You can specify conditions like and, or, not, that sort of thing, and count based on conditions. So that will give you it's a very flexible option for you to filter things in the trace, so that you pay attention only to things that you are concerned about. Okay, all right. Now I would say this kind of debugging tool is, once you know how to use it, is even superior to the use of a debugger. Okay, because with a debugger, you have to know where to put a breakpoint, and you have to know what you're watching. And by the time you press continue, if you didn't check something, it's gone already. Then you have to restart the whole debugging process just to catch that thing. If you log the right entries in this form, this is kind of like a VHS security surveillance tape of something. Okay, it's recording the whole thing. If you point the camera to the right thing, you will always find that moment. Yep.
Do you think there should be a way to do this with GDB?
Nope. Yeah, GDB doesn't have this mechanism, because well, okay, it has to do with scaling. Because with the toy processor, it is a very simplistic kind of machine, and there are only so many things that can happen at the same time. After all, we only have 256 RAM locations and 4 registers. So those are the only things that can really change. In addition, we have like program counter, instruction pointer, and so on and so forth. But there are only so many things that it can change. But when you're talking about a C program or C++ program, there you can have gigabytes of stuff that can change. So that means, to log every single thing, every single time when something changes, it's going to consume a reasonable amount of memory. So that's why it is not practical to do the same thing when you're debugging a general C program. If you're dealing with a very simple C program, oh yeah, I mean that's feasible too. But when you're debugging a realistic C program, it's no longer feasible. So are we okay so far with the instruction for today's lab? Okay. We got a few minutes left. Okay. In fact, we got 6 minutes left. So that means I actually can get started with the tracing of specific instructions. So what I'm going to do is to rewrite the program. Okay. So right now the program is kind of long because it's a loop and stuff like that. So I'm going to make it shorter this time because I want to show you what a JMPI instruction gets its job done. Okay. Oh, before that, let's check out the documentation of the JMPI instruction. Okay, so we go to the opcode table. And then we take a look at the JMPI instruction, which is this one here. And we also want to, oh, come on. My computer is just being very sleepy, very slow. There we go. This is how the JMPI instruction is documented. And you might think that, oh, it must be an error because that doesn't seem to match what we know about the JMPI instruction. Just one more, come on, up. Okay, there we go. So the JMPI instruction is saying the program counter gets whatever the program counter is pointing to, which seems really odd, right? And it seems to have the effect of branching to a location that you specify. That seems just really odd. So what we'll do in the next 5 minutes is really just to write a very simple program to illustrate how it works. So we go back to the assembler, go to source, and we'll go ahead and delete this portion because we won't need it anymore. So just delete. And since our focus is just the JMPI instruction will just do that. But we'll put some no-op instructions here just to space it out. This way we can easily tell whether we are branching or not. Okay, so this is the entire program. We go to the RAM file tab, download the CSV file, and I'll just call this jmpi.csv. Go back to the simulator, Control R, reset the whole thing, and then we go to the RAM component, load image. This is called jmpi.csv. So now we have the instruction, the instructions for this program loaded here. 4004, these 2 bytes correspond to the JMPI instruction. 00 is no op, 00 is no op, 01 is the last halt instruction. Okay, so we'll start executing this program. So, but our focus is going to be on the microcode engine this time. So now we'll do a single clock the whole thing. So single clock, and this is the execution of the jump instruction. So the jump instruction has an opcode of 40, and that's why in the ROM, the address of the microcode slice corresponding to the execution of the JMPI instruction is 40 plus one more 0. Okay. So we want to look at what things are activated at this point. So we go back to the program counter. Okay, so scroll up a little bit, and we look at the program counter. See how the program counter is already at 0, 1? Because decode is incrementing the program counter. So the decode slice of microcode is turning the program counter from 0, 0 to 0, 1. So what else is going on with the program counter? Quite a few things. It is enabled, which means it is going to be updated on the next rising edge clock. How is it going to be updated? Well, this multiplexer specifies it is going to use input 1 to update the program counter. So we now track down input 1 of this multiplexer. And that turns out to go into another multiplexer, which also has 1 as the switch or the select. So we track down this wire instead. That wire goes all the way to the RAM component. It goes to the data port of RAM. Okay? What is driving RAM? We track down the address port. It goes into this particular multiplexer. This multiplexer has a select of 1, so input 1 connects to the output of this multiplexer. And guess where that's going? Back to the program counter. That is why PC equals asterisk PC. We are dereferencing the program counter to update the program counter. But what is at that address? What is at the address that the program counter is pointing to? We got that 0, 4. What is that 0, 4? What do you think that 0, 4 really is? That's the label L1. So when we have a rising edge clock at this point, then the program counter will be updated to 0, 4, which is where the halt instruction is. So right now we have a 0 for the clock line. The next control T is going to give us the rising edge clock. Control T, you can see how the program counter is now a 0, 4. That's going to dictate where we find the next instruction to execute. Where are we going? What is at location 0, 4? The RAM component already tells you where it is. And it has an opcode of 0, 1, which is the halt instruction. So that's how the JMPI instruction works. And this is the JMP series or the J series of instructions, that is how you change the path of execution when you're writing code in assembly. We don't have if then else, we don't have while, we don't have for, we don't even have call and return. Okay? So the J series of instruction, JMPI, JMP, JCI, JZI, and so on and so forth, those are the only ways for you to specify, oh, I don't want to continue with the next instruction. I might want to go somewhere else. You have to use a J instruction, a jump instruction. So is that okay? All right, cool. So on Wednesday, what we'll do is we'll start to get into, we'll start with an explanation of how the conditional branch instructions work, and then we'll get into the structured programming part, which means I give you the C code, we translate into assembly code. We look at the C code, we translate into assembly code. It's a very systematic way of doing things. Okay, so it looks complicated at first, but once you get down to, oh, I see, we just do it one thing at a time, it is not really that difficult. All right, I'll see you guys over at the lab, and I'll stop the recorder now.